All right, guys, welcome back to another YouTube video. Today we are going to talk about some module or practice some module 3 types questions. Certain that you guys have been practicing the past couple questions already. Maybe you might be having a few challenges here and there, but let's see how much we can actually cover by looking at these particular questions. And of course, guys, don't forget to subscribe and also to hit the post notification bell. And of course, share the video and tell a friend to tell a friend about what we're doing over here. All right. So, what's what going on? All right. So we're going to start off with a question related to gases in general, more so the gas laws to some extent is being described in this question. So this is an experiment. A glass tube of cross-sectional area, 6 millimeter square, is used to study the relationship between volume and temperature of a fixed mass of gas at a constant pressure. They then went ahead and gave you the value, the table with the different data that we would have collected. So what we're seeing here is that as we're increasing the temperature, right, the overall length of the gas in the tube is going to increase, and by and large it's going to cause the overall volume to increase. So they asked us to complete the table, right, as you would imagine, to calculate the volume, right. In this case, volume would be the area times the length. Yeah, they gave you the area already, so all you would need to do is to go ahead and multiply those values. So 6 multiplied by 83 would give you 498 millimeter cube. So that's what you would have needed to do in order to get that 2 marks. All right. So please just make sure you highlight any type of values that were given to you in the worded part of the question, so that you can then think back about how you calculate the volume, etc. All right. Now, having said that, taking all of these data, you're gonna be asked to plot a graph. But they also went ahead and gave you a bit more information. Yeah. Firstly, they told you to plot volume versus temperature. Okay. So the one that is always stated first goes on the y-axis, and the other one goes on the x-axis. They told you that they want you to use a scale within this range. Yeah. So you would in essence try to ensure that your scale accounts for positive values of temperature and also negative values of temperature. By and large, the order in which you put these doesn't really matter. At the end of the day, you would still produce the same type of results. It's just that the graph might shape or would have turned a little bit differently. Yeah. So let me just zoom up a little bit for you guys to see. All right. So in this case, we're going up by practically 1 centimeter to 25 millimeter cube. Okay, and we would have plotted that graph. Now, bear in mind that in some cases you would be asked to draw a line of best fit. Just try as best as possible to get your line passing through most of the points. If not, try to evenly distribute the points that do not pass through the line itself. So like in this case, this is not completely so perfect because I only have 2 points over here that are hanging over. Yeah. So you would want one here and one over this side. So let's try to strike that balance between them. Make sure you always put your labelings on the graph. Okay. So this is where your volume would go, and this is where your temperature would go. Temperature is going to be in degrees Celsius, right? So you put your symbols there. Now, it's important to make sure that this particular graph, yeah, when you draw the line, that it actually touches against the overall you call it, the y-axis, because there's going to be a question related to that. So after doing that, so it says use the scale which shows negative 325 degrees Celsius to 100 degrees Celsius on the temperature axis, and it says they also want you to begin your volume with 0 millimeters. So you're not breaking anything. So you're going to start at 0 for your volume. Now it says from the graph, determine the temperature at which the volume is 0. So using the graph, the line that you would have drawn, so you're going to go all the way up to where it touches here, yeah? And right in between here is where you would find that particular temperature. And in this case, it tells us it's going to be negative 265 degrees Celsius, right? And this is also in degrees, as we said, all right? So that's what is happening to the volume of the gas when it is decreased, or in fact, that is the temperature of the gas when it is decreased to a 0 millimeter cube. Now it says that if the gas is cooled enough, would its volume actually become 0? Suggest a reason for your answer. So of course, we're not destroying the particles, okay? So the answer would be simply no, the volume would not become 0. And by and large, if you think back about matter in general, you know, we can't create matter, we can't also destroy them like that. And this would also imply if the volume is 0, then it would say that we have an infinitely high density gas, because think about your density formula, mass divided by volume, yeah? If volume is 0, then, you know, anything divided by 0 is infinity. So that would kind of just defy a bit of the laws of physics right there and then. And of course, you know that the mass of the gas is not destroyed in this case. So therefore, this would not the volume would not actually go to 0. It's just a more of a, you know, pictorial or theoretical type of viewpoint that the graph would be showing us what would be taking place there. All right. Now it says to determine the temperature in kelvins at which the length of the gas column would be when it is at 70 millimeters. So firstly, if you look right here on the graph, we don't have anything pertaining to 70 millimeter cube rather. So what we need to do, first we need to find the volume, yes? So we know the area already, so we're going to take the area, which is simply 6, all right, 6 millimeter squared. We're going to times that by the 70 millimeters. That is going to give us our volume. Now, once you get that volume, you're going to go to your graph, yes? You know, so this is the volume that we got, 420. So you're going to go to your graph, and you're going to find 420, wherever it is, which is right here, yeah? You're going to read off from your graph what particular temperature is associated with that. And that's how you would have gotten the answer negative, pretty much negative 55 degrees Celsius. Now, if they ask you to calculate that in kelvins, then you need to remember small formula for changing from kelvins to degrees Celsius, or from degrees Celsius to Kelvin rather. So T in this case represents the temperature in kelvins, and then we use theta to represent the temperature in what would I call it, in degrees Celsius, and then we're gonna plus that to 273.15. And once you do that, you just go ahead and plug in your values, and then you would have been able to determine the value of that in simplified version of kelvins. So let's quickly do that. Right, so this value here corresponds to be 218.15, okay? And then of course you would need to put your units, capital K for Kelvin. Question continues. You know, because we're dealing with gas questions, then we now need to remember a bit of whole aspects of gas laws, yeah, and also the equations that applies. So for an ideal gas, there's a particular equation. PV is equal to nRT, right? Or in some case, you could say PV is equal to KT, all right? Where K in this case speaks to a particular constant. I think it's the Boltzmann constant that it is, yes? That's what K would represent in this case. While R is your molar gas constant. Molar gas constant. And in fact, you would be given the molar gas constant at the front of the paper and everything, all right? Now it says outline how this equation is applied to this experiment on page 10, which is the one that we're looking at here. So first and foremost, we're plotting a graph of volume of temperature, rather. I think it's temperature. Let's look back at it. We're plotting a graph of temperature versus volume, right? So we would need to manipulate our equation in such a way that it gets us into that form of y equal mx plus c per se, right? Okay, so let's see if we can think about that. So here's our equation as you can imagine. We're seeing our p-value, so let's just kind of separate them a bit. So just as how you're seeing it here, if we make v become the subject, yeah, we'll take the p and bring it across here. It's going to divide, because it's obviously multiplying over here. So hence the reason why you have nr over p. And then, of course, we times that by t. As you would imagine, the relationship is a directly proportional relationship. And with that being said, I think we come to think of it, just want to think back about which would be the independent variable and which would be the dependent variable. So in my case, I believe that the volume would be the dependent variable. Okay. So not because the graph is plotting temperature versus not because the graph is plotting you call it temperature versus volume means that the graph is actually correct, right? It should be temperature over here and volume over here, because it's the volume that is responding based on the temperature changes, yeah? So it's kind of a messed up graph, but regardless of that, the equation that we have here kind of make it comes back together as how it should, whereby this technically should be my y variable. Then all of what is left here becomes my gradient value. And then now this becomes my y value. Sorry, my x value, I should say. Of course, because the graph, in a sense, it doesn't really start at 0, but because of the directly proportional relationship and so on, technically speaking, it would have a y-intercept of 0 per se, if it was plotted the proper way, and so on. So that's what they wanted you to do. And of course, if we are going to put the temperature in kelvins, yes, then we would need to do a bit of plusing of the 273, yeah, to make sure that everything balances out. Because with the PV equal nRT equation, your temperature has to be in kelvins, all right, at all times. And since the graph here is in degrees, then that's the reason why you would have needed to add that 273. Now moving on to 2015, it says that figure 3 shows an example of a solar panel used in the Caribbean for heating domestic water. They discuss how the principles of conduction, convection, radiation, and the greenhouse effect are applied in the design of this type of solar panel. All right, so we're thinking about water heater here. So if you look, you're seeing some copper pipes. Copper is a good conductor of of heat, and also electricity, but in this case, we're talking about heat, yeah? So by and large, when the sun's ray comes in, yeah, it will be interacting with these copper pipes, and that is where the water will be flowing through. So in a sense, because copper is a good conductor of heat, then the heat will be absorbed by the pipe, and in a sense, cause the water to be heated up. If you look at the bottom here, we have a styrofoam type of material, that is used to somewhat prevent heat from being escaped, or yeah, pretty much being escaped as it is penetrating the the copper pipes going into the water. Bear in mind now that once the heat has gone, as has been transferred to the water will then needs to be heated up. And in that process, we know that any types of fluid, yes, it's the process of convection that is used to heat up those types of fluid, yeah? And so that is what would happen. And of course, if you know anything about convection, right, as soon as the denser particles, which is the water molecules here, gets hot, they're going to rise and create that cycle, as you can imagine, yes, in the whole system. So you find that the hotter water is going to rise, and that water then can be pumped manually or naturally based on how hot the overall heat is, so to speak. Overall, yeah, pretty much how hot the overall system is. So that will, in a sense, kind of give the water a bit of a push to go into the different systems or into the storage container. Now, in terms of the radiation, in most cases, well, if you look on the diagram here, it says that it is a section of it that is painted, right, in, or it says blackened copper plate. So there's a particular plate that sits behind of the copper pipings, that, because black is a good absorber of heat, yeah, it's going to absorb a lot of heat within that region so that the copper pipes can in a sense, retain most of the overall heat that is coming from the sun itself, yeah. Now, in terms of the greenhouse effect, it's for you to understand that once, because there's a glass casing that surrounds the overall copper pipes, so when these light rays, yeah, comes in this case, we're thinking about the short wavelengths infrared radiation. Infrared radiation is that one that generally carries heat, right? So when those short wavelengths comes in, right, and penetrates through the glass itself, the glass is going to kind of refract it and slow down the light in itself. And for that reason, you find that when the light is absorbed by some of the items inside, like the copper rods and so on, you're going to have that some of the light rays are going to be reflected and so on, yeah? And in that process, longer wavelengths will be produced in that process. However, when those longer wavelengths are produced, right, they cannot penetrate back through the glass. So in a sense, that overall heat or that particular long wavelength is then trapped within the overall container here, or the overall enclosed glass surface. So you find out that the heat, that came in will be more so wanting to be retained within the overall system. So the heat is then trapped, and that gives rise to the overall greenhouse effect. And I mean, I think you all should make sure you revise that. All right. Now, quickly, let's see if we can talk about another type of question. This mainly has to do with the rate of heat transfer. So it says that a wall of a cold store is constructed from 2 layers of brick with a foam-filled cavity between it, as shown in figure. It says each of the layers of the brick walls is 10 centimeters thick, and the foam cavity is 5 centimeters wide. It says on a typical warm day, the temperature outside is 30 degrees Celsius, while the temperature inside the cool room is kept at -5 degrees Celsius. It says sketch a graph to show how the temperature would vary across the wall. Okay, so by and large, you should know that in this case, the brick would kind of be like a material that allows heat to pass through it quite quickly. Yes, it's not an insulating type of material. So you're going to find that the rate of heat transfer is going to happen quite quickly. Yeah. going to happen very quickly. So we're not going to have much decrease in our temperature. So this type of graph that you're really plotting is what we call a temperature gradient graph, which just kind of outlines how the overall change in temperature occurs as it travels from one end to the other. Now, when it reaches the foam is very much of an insulating material, and that in itself will pretty much prevent or makes the rate of heat transfer take much longer based on the thermal conductivity of the material. So if you look here, right, it tells you what the thermal conductivity of this particular material is, right? This is a 0.48. So the brick has a much higher thermal conductivity, which is just the ability for the material to conduct heat, whereas the foam has practically 0.016, right, in terms of its thermal conductivity. So it has a much lower thermal conductivity ratio. So therefore, when it reaches to the second brick layer, you're gonna have the same rate of heat transfer taking place because of the fact that same materials and also same thickness and everything. So that is that. Now the question then continues and said that the thermal conductivity of the brick is 0.48 watts per meter per Kelvin, and that of the foam is 0.016 watt per meter per Kelvin. It says calculate the thickness of the brick, which would have the same insulating effect as the 5 centimeter of foam. So by and large, right, you need to remember the overall equation to some extent. But before we talk about that equation, in this question, you should understand that the rate of, well, not the rate, but the thermal conductivity of the brick is way higher than that of the foam. Okay, which explains why the gradient here is very gentle for this particular graph. So what we'll need to do here is to just find out how much times more is the thermal conductivity of the brick is when compared to that of the foam. And to do that, we just simply divide the 0.48 by the 0.016, and then we would get that, in a sense, the brick has 30 times more thermal conductivity in itself than that of the foam. Okay, so if that is the case, then in order for us to know what thickness of the brick that would be required to have the same effects, same insulating effect, right? We would now need to take into consideration the thickness of the foam, yes? And so if the foam has a certain heating effect, yeah, of 5 centimeters, then for us to know how much thickness we're going to require for this particular brick, since the thermal conductivity is 30 times that of the foam, then it's the same thing that's going to happen to the thickness. The thickness has to be 30 times greater than the thickness of the foam itself. So for that reason, the overall thickness in this case, right, has to be 150 centimeters. All right. Now for this question, they asked us to determine the rate at which the heat energy would pass through each square, right? We want us to find the rate at which the heat is. Now, this particular question wasn't the best. This is the equation that you would, by and large, use to solve the question, but I'm not getting how they would get the particular um, change in the thickness, right? So if you can figure it out, then that would be good. So this is the overall equation that you would use to calculate the rate of heat transfer in conductors per se. We know the thermal conductivity, of course, which is 0.48. They told us it is a square meter of 1 meter. Sorry, they said that it's for each square meter. So the area is technically 1 meter square. In terms of the change in temperature, we know it is decreasing from 30 to negative 20, -5 rather, right? So we kind of know the overall change in temperature and everything. But this part here is where the challenge lies, right? I'm not sure how they would have calculated this part really, okay? But if you can figure that one out, that would be good. Now let's quickly talk about thermometers in itself. So it says a resistance thermometer and a thermocouple thermometer, in a sense, are both used at the same time to measure the temperature of a water bath. It says explain why the thermometers may record different temperatures, even though they are calibrated accurately and are at equilibrium. So different thermometers are made using different types of properties. As you can know, there's what we call thermometric properties. These are simply physical properties that changes when temperature changes as well. So like resistance, the next thermocouple has to do with voltage or EMF, yeah? Thermocouple has to do with EMF, and this has to do with measuring the resistance, which is obviously measured in ohms and those things. Each of these are constructed differently, right? Or the properties that surrounds them are different, or they react differently with temperature. The next thing is that not all thermometric property gives you a directly proportional relationship as most thermometers does. Like take for example a liquid in glass thermometer. That one will always show you a directly proportional relationship between the height of the liquid and the change in the temperature. But not all of them. Like for a thermocouple, in most cases the graph goes up and then it starts to curve or something of that nature. I don't remember quite exactly what it is, but you know that the graph can curve, you know, and sometimes you have to use like a curve to figure out the temperature and so on. So that's the whole reason why the temperature could change in this case. They then ask you to define or what to explain what is meant by the absolute zero. So absolute zero is by and large the lowest temperature that can be measured, right? Or the lowest theoretical temperature that can be measured, and that is, of course, 0 kelvins, and on the degrees aspects, it is negative 273 Celsius degree or degree Celsius. And you can become a bit more creative and put the 0.15 if you want. Now it says state how the absolute thermodynamic scale of temperature differs from other temperature scale. When it comes on to the absolute thermodynamic scale of temperature, is that one only has one fixed point, whereas the other temperature scales have multiple fixed points. So like when you think about your liquid in glass thermometer, right? Those scales are based on what we call the melting point, the boiling point, and so on, yeah? Those are generally the fixed points per se. But when it comes on to like the thermodynamic scale, which just speaks to the overall movement of the particles themselves, yeah, the only fixed point that we can talk about is what we call the triple point of water, right? When we're dealing with the absolute thermodynamic scale. And by and large, when we talk about the triple point is just simply that temperature at which all state can coexist at the same time, right? And this is just a kind of a sketch of a graph that kind of shows us. So like for one particular region up to a point, you know, we're going to have our solid state, and then at a particular temperature, and yeah, at a particular temperature, the triple point just defines or tells us simply that all three states of matter can exist or coexist at this point, yeah? Now the critical point here is just like that point where the gas is at a very, very high temperature where it now changes from gas to some other type of state of matter, okay? By and large, you should note that the triple point of water is 0.0 1 degrees Celsius or Celsius degrees. Yeah, that's what the triple point of water would be. So in a sense, triple point just speaks to the temperature at which all three states of matter can coexist. Okay, now the question then asks us to, in a sense, calculate the temperature in kelvins and so on, yeah? And of course, they want to use appropriate significant figures, given the fact that we have 2 decimal places here within these in these figures, we should put it back as such. I think by now you know the equation. So T is equal to theta plus 273.15. Yes. Then you would change that temperature to 50 degrees. So you add 50 to that. And we get our value in terms of Kelvin. Now, what if they ask you to find overall change in temperature of the water bath? So we're seeing where that the water bath is increasing from 50 to, in a sense, 30. Sorry, from 50 to 80. So that overall change is going to be 30 degrees Celsius. Now, the beautiful thing about Kelvin and the degrees Celsius scale is that while there are 2 different types of scales, they still have an equal increment each time. So for every change that happens in Kelvin, it's the same amount of change that happens in degrees. So, and how we can prove that is by changing this 80 degrees to Kelvin. Yes. So if we do that, you're going to see that when we do subtract it, it's still going to give us the answer as 30, because we find that the changes in degrees Celsius and Kelvins are practically equal values. So in terms of this value, it's 353.15. We're going to subtract that by the 323.15, which gives you 30. So the answer in degrees Celsius is still going to be the same answer in Kelvin, because you're dealing with a change in temperature here. Okay, now it continues and tells us that an empirical centigrade temperature can be determined and defined in terms of any suitable thermometric properties. So this is like another way in which we can calibrate temperatures, right? Now it says select one type of thermometer with suitable thermometric properties. And we said thermometric properties are those that changes with increases in temperature, and describe briefly the procedure and the necessary readings that you would take in order to use this thermometer to measure the temperature of a random temperature per se. So generally speaking, when we talk about the centigrade scale of measuring temperature or whatever, it's one that measures the temperature at the fixed points, right? So we have the melting point, we have like the boiling point. Cool. So you can by and large know when you're at those melting points well, you can know when something is at the melting point, and you can know in time something is at the boiling point, because those are physical changes. So first, you would need to determine how the property expands when it is at its upper fixed point, which is the boiling point. Yes, thereabout for that particular what do you call it, substance that you're trying to measure the temperature of. Of course, in some cases, you have to kind of either use some reference that you already know. Well, of course, you can know in time something is at its upper fixed point because you would see it boiling. So it doesn't have to be water. You know, water, in a sense, was the 100 degrees for the most part under the circumstances that pressure and everything is kept at relatively fixed values per se. But for any substances, you can know the upper fixed point. So what you would need to do is to note how much the liquid in the glass thermometer is going to rise by when it's at its upper limit. And that would be considered as, in a sense, the temperature at, in essence, at 100, because we're looking at it on a centigrade scale. So a centigrade scale is where now you are, in a sense, you're going to divide up those values, equally up to 100 or whatever, in a sense, 100 distribution along the scale itself. The next thing is obviously to determine the property. All right, in this case, it's the length that we're looking at, or the liquid in the volume of the liquid, or the length of the liquid in the glass thermometer at its fixed point, right? Which at a lower fixed point, I should say. So that would be like at the freezing point. So you're gonna either cool down the system so that it reaches to that point where it becomes like a solid now, where freezing start to take place. So you want to note how much that change in property occurs. Then for the unknown, but to determine the unknown temperature of that particular substance now would be for you to use a formula here, right? So the formula that we can use to figure out the temperature in degrees using the centigrade scale is this formula here. So this is what you're trying to find, okay? Sorry, that's not what you're trying to find. This would be the property at that temperature. So whether it be that the length, right, the length of the liquid in the glass thermometer. So you would have that length there. Maybe it's 100, or maybe it's 25. Who knows? Whatever the length might be, depending on what temperature it's at. Then you're going to subtract that by the temperature at the lower fixed point. Divide that by the temperature, or sorry, not the temperature, but more so the property here, the property. So we're looking at the properties in this case. So in terms of, let's just look at an example. So imagine that we're dealing with length here, and this is temperature or whatever. And I want to find out the temperature at this point. These are my fixed points, 0 and 100. Cool. But of course, this would be like a length of, let's say, 25 here, 25. And then this would be like at, let's say, 10. Okay, let's say 10. And then now, this particular length is going to be, let's say, 15. Cool. Now, the idea is to take those values. So we're going to take the 15. We're going to subtract that by 10, We're going to divide that by 25. We're going to subtract that again from 10, which would be the value of the property at the lower fixed points. And then you times that by 100, and it will give you the value of the temperature in degrees. All right. Moving on. So I want us to talk about Young's modulus. This is a 2015 paper. It says Young's modulus is defined as a ratio of pretty much the stress of a material to the strain of that material. So think about expanding or stretching an elastic. Yeah, that elastic will have a Young's modulus because it's experiencing stress and it is also experiencing strain at the same time. Of course, you need to remember these things, how you find stress and what's the unit for stress. Stress is like having pressure, is calculating pressure. So force over area is what stress is. Strain is just the ratio of extension over the original length. That's what strain is. So at the end of the day, this is what your Young's modulus equation is. You get about 3 marks for that question. Now it says explain the differences between elastic deformation and elastic deformation, and it says make reference to Hooke's law and also the energy changes in the material. So firstly, when you have elastic deformation, you find that the object returns to its original length when the load is removed, and of course the energy that was stored is recovered when it returns to its original length. And this means that the object would be obeying Hooke's law, because Hooke's law tells you that force is directly proportional to the extension. All right. Now, for the inelastic deformation, or in other words, plastic deformation, is when the object does not return to its original shape, so it's more deformed in terms of the fact that, or in other words, permanent deformation takes place, okay, when the load is removed. And of course, the energy that was stored is not, all of it is not going to be recovered. Some might be converted into heat when it is stretching the body, and therefore, beyond that region, Hooke's law does not apply. So beyond the region where elastic deformation takes place, Hooke's law does not apply there. Okay, it says a bone has Young's modulus of, in a sense, 1.8 times 10 to the 10 pascals. Under compression, it withstand a stress of 1.5 times 10 to the 8 pascal before breaking. Okay, so rather than talking about extension, we're talking about compression, which is kind of like the same thing, okay? But more so, it's not necessarily the same thing, but it's that's what you're gonna really try to find in this case. So you know, with the equation that says strain is equal to extension over the length, the compression in this case would in essence speaks to the extension. Really, it's not extending, but it's more so compressing, so it's decreasing. They want us to, they tell us how long the femur was, 0.47 meters, and then they want us to calculate the amount that it has extended by, or sorry, it has compressed by, I should say, before it breaks. So first thing first, we're given some information. So you write down what was given. So you're given the Young's modulus, and bear in mind the units for the Young's modulus is same thing as pascals. This is the maximum stress that it can attain. We know the length of the system. So all you need to do is to make strain become the subject. So strain is equal to stress over the Young's modulus. Cool. We can find the stress. Sorry, we can find the strain by just plugging in the value. So 1.5 times 10 to the 8 divided by 1.8 times 10 to the power of 10. You will get your strain at that point. Once you get that particular value, you know that strain is equal to extension over length. So E is equal to length times the strain. So whatever value you got here, you take that value, you multiply it by the length, which is 0.47 meters, okay? And that should give you your overall extension. All right. Question continues. And it says to us that we have a crane set up here, right? And we see some cable attached to some type of load over here. So now it says that the motor in the crane lifts a mass of 1,800 kilograms, right, from rest on the ground. Now it says that the cable supporting the mass is made by steel that has a Young's modulus of 2.4 times 10 to the 11 pascals. The cross-sectional area of the cable is practically 1.3 times 10 to the minus 4 meter square. As the mass leaves the ground, the strain in the cable is this amount. So you know the cable is very, very stiff. Good. It says assume that there's negligible weight of the cable. That is not adding any further strain to the overall system. Use the Young's modulus. Use the Young's modulus of the steel to determine the tension in the cable. So I mean, if you can remember anything, know that Young's modulus, we're going to use Y is equal to stress over strain. All right. We weren't given the strain. You know, if we were given the strain, we could just use force over area and find it out. But we're gonna have to break down this equation. So we know that stress is equal to force over area, and that is also divided by E over L. But we can further restructure this in a form that looks like this. Yes. Anytime we're dividing fractions, we can find the reciprocal of the second fraction. So we end up with this structure. So we can now kind of further manipulate that. We can make F becomes a subject. And if you follow with this note that you have down here, then you would see that F is going to equal to the Young's modulus times the area times E over L. Depending on how you want to do your maths, but at the end of the day, just make sure that you're doing everything properly. Cool. And then you just plug in your values. I would suggest that you probably make F becomes a subject first with the variables, and then you plug in the values after so that you don't get confused. So like in this case now, since this is equal to, right? So this is equal to this. And in fact, I didn't have to do it this way because I mean, it seems a little bit longer here, but just so you know, yeah? So we would get rid of this, which will take the E over that side. So we have Y times E over L. And because it's also, F is being divided by area, I have to multiply both sides by that. So that's how we're going to multiply the area over here, which is what we have right now. But we already know the strain. We already know the strain, you know. See that we know the strain, so I didn't have to do all of that. We know the strain already, which is this, the extension over L. So yeah. Now it says assuming rather, it is an 8-ton crane and the length of the cable is 8 meters. Determine the extension in the cable when the crane is operating at its fullest load. Okay. So what you should remember is that 1 ton is 1,000 kg. So therefore we have 8,000 kg here, so we can find the overall force that is supported by the cable. Cable length is 8 meters. So still using the whole Young's modulus scenario. You know the Young's modulus already of the steel, which is 2.4 times 10 to the 11, right? So you take that value and everything, and then just rearrange your Young's modulus equation. Make E becomes the subject. There and then you would see that the extension is just going to be roughly 2 centimeters. All right, guys, so that's pretty much complete these past paper questions on module 3. Hopefully, you know, it was helpful for you guys. There are a lot of things left for module 3 that you probably should be revising, such as thermodynamics. Yes, it shouldn't be that difficult, but make sure you're researching your what does the adiabatic graph looks like, your isovolumetric type of graph, and your isochromic graphs looks like in terms of um, pressure versus P pressure versus volume type of graph, the PV type of graph, and also remembering that it's the area underneath the graph that tells you the work that is being done on the gas and so on. So those are some ones that you should be revising. But guys, don't forget to comment and don't forget to subscribe and like the video, and of course share it with others. All right. Thank you guys. Have a wonderful day.